Hi class, welcome to day one of calculus. My name is Mr. Scrunchy. We're going to go through the notes. So I'm going to put down my key. What is a function? You should know that for every x, there's exactly one y value. X is the domain, y is the range, x is the input, y is the output. So we have horizontal asymptotes. So a horizontal asymptote should look like this. So a horizontal asymptote is when one or both of the ends of the graph will level off to some specific y value, like y equals 5. So right now, this is an HA. X goes to infinity is the right side of the graph. X goes to negative infinity is the left side of the graph. And in this case, I have both sides leveling off to whatever value. A lot of times, we do a leading term over leading term when we're talking about rational functions when we have polynomials involved. Something like a 3x squared over x squared will give y equals 3 as an HA. So that's really what horizontal asymptotes are. Vertical asymptotes are the other way. We're looking for a specific value of x, and the y values are either going up to infinity or down to negative infinity on either side of the VA. So you see my red dashed VA here. On one side, the graph is going down to negative infinity. On the other side, the graph is going up to positive infinity. So we say as x approaches a with the little plus sign is from the right side, and as x approaches a with a little negative sign is from the left side. And either side of the VA, the graph is going up forever or down to other, depending on what you want. Limits for end behavior is the right side is infinity, the left side is negative infinity. Vertical asymptotes horizontal asymptotes are an example of end behavior. But the end behavior doesn't have to be level. The end behavior could be up or down forever. Sometimes there's no end behavior if you remember your sine and cosine graphs. And then we have limits at one specific point, x equals c. So we have, from the right side, we have the little plus next to the number c. From the left side, we have the little minus by the little number c. And then in general, it's both sides. Not the left, not the right, both together. That's the generals, x approaches c. So if something has a limit, that means the right side has to equal the left side. That means the limit will exist. So if the right side equals the left side, we do have a limit in general. But if the right side does not equal the left side, so let's say we have a graph that looks like something like this, you could see the left side and the right side of the graph are not meeting together at one specific point. That's when we say the limit does not exist. Let's do some examples on the next page. So looking at this example of a graph here, we're going to do some values and some limits. Every single answer for this, every single response to these questions will be y values. F of 0 and f of 1 are value questions. They want a solid point. So at f of 0, right here is x equals 0. There is no solid dot, so this is undefined. And at f of 1, we don't have a solid dot here. The solid dot is way up here at 4. Those are value questions. It wants a solid point. Limit questions are the intended y value. That says if you get closer to that x value from the left or from the right, like here is 0, so from this way, this is 0 from the left, and this way is 0 from the right. We say 0 from the left gets closer and closer to y equals negative 1. It never really gets there, but it gets as close as possible. And from the right side, I again have y equals negative 1. And then right here is the general question of 0, not from the left, not from the right, from both sides. And my left side and my right side are equal to each other. So it is negative 1. The left side and the right side are meeting together at y equals negative 1, even though it never really gets there. Now let's look at 1. Right here is 1. I'm going to change color here for a second. I'm going to change it to purple. At x equals 1, from the left side, it's right here. It is getting closer to 0. And the right side, it's right here. It's getting closer to 2. But I notice my left side does not equal my right side. These two do not equal each other. So whenever that happens, that means in general, x equals -1, it is DNE. The left side and right side are not meeting together. Okay, the next part is looking at continuity. What makes something continuous? Well, you could tell this graph is not a continuous graph. It has breaks in it for sure. But there are points that it is continuous. So the whole idea of continuity is this funny word, not lifting up your pencilability. But you have 3 conditions. 1, the value must exist at that x value. 2, the limit must exist at that x value. And 3, part 1 and part 2, the value and the limit are equal to each other. So if we look at the example at x equals 2, part 1, f of 2 is equal to 4. That is for sure. Part 2, the limit as x approaches 2 of this function is also equal to 4 because if you look at the left side and the right side, the left limit is equal to 4 on the left side of 2, and the right limit is equal to 4 on the right side of 2. So together they equal 4. And then finally, part 1 does equal part 2. So this graph is continuous at x equals 2. It's not continuous for the whole thing, but at x equals 2, it is continuous. There's no break there. Let's talk about different types of discontinuity. Obviously, this graph that's above that I can't see anymore is discontinuous, but there are different types. One is called removable discontinuity because there is a hole in the graph, just a hole. We had this many times. If you look at x equals 0, you saw you had this type of graph. This is at x equals 0, okay? This is called removable because if all you did was take your pencil or marker and put a dot right there, it would now be continuous. It's very easy to just put in a solid dot to make it continuous. But using the 3 steps, step 1, f of 0 is undefined. Step 2, the limit as x approaches 0 was equal to -1. And step 3, part 1 does not equal part 2, so it's obviously not continuous. Jump discontinuity is kind of when you have a gap. If you look at x equals 1, you kind of have this thing going on. Little part of the graph, a little jump, little solid out here, and that's x equals 1. At part 1, you had f of 1 was equal to 4. That's good. Step 2, the limit as x goes to 1. That was DNE because the left side did not equal the right side. So obviously step 3 is part 1 does not equal part 2. So at x equals 1, the graph is not continuous. Other types of discontinuity is called infinite. It's when you have a vertical asymptote. 1 over x. 1 over x squared. If you notice, they have vertical asymptotes right here at x equals 0. So it has an infinite discontinuity. It's not a gap where you could just pull one graph on top of the other, or there's a missing dot or this and that. This is infinite discontinuity. And some things you should remember from your Algebra 2 days: a function is increasing if there's a positive change in f, or the rate of change, I'm going to abbreviate ROC, is positive. It's decreasing if the rate of change is negative, and it's constant if there is no change in the function or ROC is 0 via horizontal line. In rate of change is this most important idea. Not only does it tell me if a function is increasing or decreasing, it also tell me its concavity. Something is concave up if it has a positive change in rate of change, or the rate of change is increasing. It's concave down if the rate of change is decreasing. And there's 0 concavity if it's a linear function or if you have an inflection point. So let's look at some of these graphs. So I have 4 different graphs here, and the one that is going up and curving up has a rate of change that is positive and increasing, or the function is increasing at an increasing rate. The next one has a rate of change negative and increasing, so it's decreasing at an increasing rate. The one that's first one that's concave down has a rate of change that's negative and decreasing. It's curving down, so it's decreasing at a decreasing rate. And the last graph here has a positive rate of change and curving down, so it's increasing at a decreasing rate. It's all different ways we can talk about the same idea. Concave up is a increasing rate, concave down is a decreasing rate. An increasing function has a positive rate of change, a decreasing function has a negative rate of change. Extrema or extremes are just a fancy way of calling mins and maxes. And you have absolute mins and maxes, or global mins and maxes, or local or relative mins and maxes. So a bottom of a parabola would be an absolute global minimum. The top would be a absolute or global maximum. And the relative mins and maxes are the little peaks and valleys in between. Boundedness may be a new word. I call it's a boundary or a fence that could be above the graph, below the graph, or both. So bounded below means there's a bottom boundary that the graph never crosses. This first graph will never get below that bottom boundary. That means it's bounded below. Obviously, this is a top boundary. And this one has both a top and a bottom boundary. So like a sine graph, it's bounded. Not just below, not above, but both above and below. So symmetry, there's even symmetry, there's odd symmetry, and there's no symmetry. Even symmetry is like a parabola that could be reflected over the y-axis. Odd symmetry is like a sine graph or a cubic or just the line function through the middle. You can rotate it 180 degrees. But we're going to look at some things algebraically. What I'm going to do, I'm going to plug in negative x. And the idea is that something is even is that when I use a negative x, I get the same value as before. And odd symmetry is that when I use a negative x, I get the opposite of what I had before. It's the complete opposite. And no symmetry is that I don't get either one. It's not even, it's not odd, it's none of the above. Okay, so I plugged in negative x for all these examples, and you could see that when I plug in negative x, it's the same, it's even. You plug in negative x, it's the opposite, it's odd. These are opposites. Fractions are opposite when the numerators are opposite, because if you added them together, they would be 0, and the last one is neither. So these characteristics you should be able to do. I'm going to go through it for a second, but I'm going to pause the video and just put up the solutions to everything. But these are characteristics you should know. We're going to use interval notation. If you don't know interval notation, you better come and see me sometime, because this is the basis that we're going to use all year. So the domain is all the x values, and I know there's no arrows on this graph, but it goes on forever, negative infinity to infinity. The range are all the y values, and again, it goes up and down forever, negative infinity to infinity. Now I'm going to pause it and do the rest. So looking at the example of a linear function, it is always increasing left to right. It is never decreasing. F of x greater than 0 is when it's above the x-axis. That's 0 to infinity, the right side half of the graph, and it's below from negative infinity to 0. Since it's linear, it's no concavity. The right side end behavior of x goes infinity goes up to infinity. The left side goes down to negative infinity. Almost made a mistake there. No asymptotes. The x and y intercepts are both 0, 0. It is an odd graph because you can rotate it 180 degrees. It is continuous. There's no breaks in it. And it is unbounded. Let's try the quadratic, the parabola. The domain is still negative infinity to infinity, but the range is not. It is 0, brackets, including 0, to infinity. It is increasing and decreasing. While it's increasing on the right half of the graph, it is decreasing on the left half of the graph. I'm going to pause it and do the rest. So I filled in the rest of the information. The big thing is that it's an even function. It's bounded below. You can see there's nothing below the x-axis. It is only above the x-axis almost the whole time except at the point 0, 0. So I just did not include that. And if you go back to the example 1, example 2, x is x to the first, which is an odd exponent, and x squared is obviously an even exponent. That kind of helps you with even and odd. So we're going to use this graph to do all these limits. Remember, limits are y values. It tells you what x to go to, and your result is a y value, or it could be a DNE. So when I do this problem, it says the limit is negative 3 from the left. The little minus sign is from the left. Right here is negative 3, and negative 3 from the left. This y value is 4. 3 from the right. This y value, negative 3 from the right, this y value is also 4. And since both the left equals the right, when x goes to negative 3 in general, the answer is 4. But then it asks, what is f of negative 3? And that wants a solid point. And there's no solid point right here at 4, but you go way up here, there's one at 13. And then x goes to negative infinity as x goes to infinity is the far right side of the graph. If you look at this far right side of the graph, go farther right, it is leveling off at y equals 8. And then this is the far left of the graph. I go farther left, not over here left, far left. This graph is going up and up and up forever to infinity. It says negative 1 from the right. Well, right here is negative 1. And from the right side, that means I start on the right side, I come back to negative 1. I'm dragging my marker back to negative 1. I get 6. This is negative 1 from the left. That result is 12. Even though there's an open dot there, open and closed dots do not matter for limits because I only have to intend to get there. I don't have to get there. But since the right does not equal the left, this limit in general is DNE. They don't meet together. F of negative 1 wants a solid dot, and the solid dot is at 6. It says 2 from the left. So I come to 2. And on the left side of 2, this graph is going down to negative infinity, and on the right side it's going up to infinity. Kind of gives it we have this kind of vertical asymptote at x equals 2. So this last one I'm going to let you do on your own. I'll put the results up after I pause the video. But hopefully you should be able to do this. No problem. So hopefully you got all the results. Please, since we're in class, whether you're here live or remotely, I'm on Zoom. Please come to Zoom, ask me questions. We could bring things up. I understand if you weren't at Gilmore Academy last year and we did a lot of extensive work with limits. But if you did not, that's okay. The first unit is mostly a review units. But please ask questions. Okay, thank you very much for watching this video.